Hello, this is Rhik for MathEx, and today we'll be doing number 7 from the AIME I of 2020. Now, this number 7 on the test was very controversial because for some people it was ridiculously easy. It was like a textbook problem to them, while for other people it was mind-bogglingly hard. And the reason for this is this problem can be solved using an identity called the Vandermonde identity. However, this identity is not commonly known, so the people who knew this identity could easily just apply it and use it to solve this problem with ease. But the people who didn't know it, well, they have to struggle through and try to find some other method. Today, I'll be solving this problem using the Vandermonde identity, and I will hopefully show you how easy to understand this identity is. So if in the future, if another problem like this comes up, you'll know how to combat it using the Vandermonde identity. A club consisting of 11 men and 12 women needs to choose a committee from amongst its members so that the number of women on the committee is one more than the number of men on the committee. The committee can have as few as 1 member and as many as 23 members. Let n be the number of such committees that can be formed. Find the sum of the prime numbers that divide n. So, the problem tells us several things. It tells us that we have to choose a committee from 11 men and 12 women. But we have to make sure that the number of women on the committee is exactly 1 more than the number of men on the committee. And it tells us that this committee could range from having 1 member to 23 members. So we can start the problem, and starting it off isn't that hard. We just need to run through all the cases and then sum them up. The first case is when there's 0 men and 1 woman. We can express this as out of the 11 men choose 0 times out of the 12 men choose 1. The second case we need to take into account is pick 1 man and 2 women. So 11 choose 1 times 12 choose 2. The third case is 11 choose 2, picking 2 men out of the 11 men. And then, since we have to pick 1 more, picking 3 women out of the 12 women. And we see there's a pattern here. No matter what number of men we pick, we have to just add that to 1 to get the woman. Just like the problem tells us, we're supposed to have 1 more woman than every man. So then, since we already predict the pattern is going to look like this, we can go to the final term. The final term is going to be when we pick 11 men from the 11 men and 12 women from the 12 women. And this is where it gets tricky. Each of these are individual cases. So the number of committees that can be formed is just the sum of all these individual cases. So if n is the number of such committees, the sum of this is equal to n. As for how do we find the sum of this, well, that's a whole other difficult thing. We could try bashing it out, but we can see very quickly that the numbers get really big. The first term's not so bad, because 11 choose 0 is 1, and then 12 choose 1 is 12. The second term's slightly worse, but not impossible. 11 choose 1 will give us 11, and then 12 choose 2 will give us 66. 12 times 66, well, that's going to give us something. But then we see the numbers really get out of control, so that is not a viable method to do it. Now, this is where Vandermonde's identity comes in. Vandermonde's identity states that if we have numbers in the form of m choose r and n choose k minus r, then the sum of them from when r is equal to 0 to k is going to equal to m plus n choose k. And we don't really understand what this statement means until we decontextualize what this theorem is saying. So to decontextualize it, let's think about it like this. We have a class of m plus n students. M girls and boys. And we want to pick a group of k students out of them. Well, one way we could do it is just by picking k students out of n plus n total students. So that would be the n plus n choose k. However, we could also do it by finding all the ways we could pick the girls and the boys and then multiplying and adding all these cases up. And what this would look like is if we wanted to pick 0 girls for one case, 1 girl for one case, 2 girls for one case, 3 girls for one case, and then we would range through that. And the same thing, we would find the corresponding number of boys so that the sum of the girls and boys would add up to k. Vandermonde's identity states that the sum of all these little multiples will just add up to the larger case. So the left-hand side of the equation basically states that the sum of all the ways you can pick little groups for each of these things and corresponding groups for the other one, the sum of all these cases is just the same as picking one big size group from a big quantity. Now, how do we apply this theorem to this problem? Because if we look at the terms, we realize that we don't really have like a k minus r term here. There's no common k that these two numbers would add up to, along with these two numbers and these two numbers. And this is where you have to be slightly creative. The thing about choose is that it can be written in multiple different ways. For instance, 12 choose 1 is not only written as 12 choose 1, it's also equivalent to 12 choose 11. And this is just another property of factorials. Remember, 12 choose 1 is just 12 factorial over 1 factorial times 12 minus 1 factorial, which is 11 factorial. And we can do the same thing for 12 choose 11. 12 choose 11 is the same thing as 12 factorial divided by 11 factorial times 12 minus 11 factorial. 12 minus 11 is 1. These terms are the same except for the order that this comes in. However, by the commutative property of multiplication, this doesn't make a difference. So we can actually rewrite all these smaller terms in terms of their opposite values. So this 12 choose 1, we can rewrite it as 12 choose 11. 12 choose 2, well, this can be written as 12 choose 10. 12 choose 3, that can be rewritten as 12 choose 9. And the 12 choose 12 can be written as 12 choose 0. So now we see that the bottom parts of each of these choose functions adds up to a common thing. 0 plus 11 will give us 11. 1 plus 10 will give us 11. 2 plus 9 will give us 11. So we have our k in this case. The common sum they come up to is 11. So our answer will have 11 as the number that's going to be chosen from the larger set. We can get the m and the n by looking at the m and n in our case. In Vandermonde's identity, the m and the n always stays the same, and they're just the two numbers always on top. In our case, we see that 11 and 12 are always on top. So we see that the m and the n are 11 and 12. So we see that applying Vandermonde's identity to our equation that we slightly altered using choose notation, we get that our answer for the sum of this value will be 23 choose 11. So the number of ways that you could pick a committee from 11 men and 12 women using the criteria stated in the problem is 23 choose 11. However, the problem's asking for the sum of the prime factors. So we have to expand this and find how many prime numbers are in it. So 23 choose 11, just like all choose functions can be written as 23 factorial over 12 factorial times 11 factorial. Then if we simplify this by canceling out the 12s from the bottom and the top, we get this is equivalent to 23 times 22 times 21 times 13 over 11 factorial, which is just 11 times 10 times 9 times 5 times 4 factorial, which is 24. 4 times 3, which is 12. 12 times 2, which is 24. And then the question asks, not for the value events. We don't have to multiply this all out, thank God. But we have to find the sum of the prime factors in this. So we just need to divide this and simplify it as much as we can until we're just left with the product of numbers. From there, we can just dig out the prime factors. So let's just divide this. If we take out the 11 from the bottom and top, we're left with the 2 where 22 was. If we take out the 10 from the top and bottom, we're going to be left with 1 here. And then if we take it out from the 20, we're going to get 2 here. 9, we're going to get 2 where the 18 was. If we divide the 8 from both sides, we get a 2 where the 16 was. 7 from both sides, we're left with a 2 from where the 14 was. 6, well, that's a little harder to find because we don't have any clean multiples, but if we look at 21, that's just 3 times 7. So if we take out a 6, we just need to take out a 3 and a 2. So let's just take the 2 from the 22 and then the 3 from the 21. The 5, well, we have a 15 left over, so we can take the 5 out from there, and we're left with 3. And then we have 24. This is going to be a tight fit because 24 is 2 to the 3 times 3. So we have to pick up 3 2's from the top part, and then we have to pick 1 3. Luckily for us, we have exactly 3 open 2's right there. 1 here, 1 here, and 1 here. And then we also have a 3 to go along with it. So we can divide these pretty well. So then we're left with the prime factors being 23, 7 from the 21 that never got used, 19, a leftover 2 from the 18 that was never used, 17, and 13. So these are all the prime factors we found that go into n. Our final job of the problem is just to add them all up, and then from there we'll get our answer. 23 plus 7, well, that's 30. 17 plus 13, another 30. And then 19 plus 2, 21. 30 plus 30 is 60, and then 60 plus 21 is 81. So we get 81 to be our final answer. So, in essence, this is an AIME problem, an AIME number 7. So this problem is quite difficult. It's an AIME problem, American Invitational Mathematics Exam. But if you know Vandermonde's identity, the bulk of the problem, this huge choose sequence, can be solved really simply. And the Vandermonde's identity is not even that complex. However, if you understand and know how to use it, these kinds of sequences can be summed up really easily. Once we got this sum, we just had to do some easy computation and take some prime factorizations, and adding it all up, we would get an answer. The key thing I want you to take away from this video is Vandermonde's identity. This important principle. This entire principle just says that picking k objects from a group of m plus n is just the same as all the different parts. We could pick one small part, r, where r is 0 through k, from part of the group, times all those times we can pick 0 through k minus r from the other part of the group, and then just adding these up. The sum of all these little group cases is just going to eventually equate to the larger case. This idea behind Vandermonde's identity is not particularly complicated. It's just very useful. So in the future, if you see another problem with a large sequence of choose notation, remember Vandermonde's identity, and then the problem will fall apart, making it really easy to solve.